Okay, so I guess the interest was to look at so a specific kind of analysis that was part of a discussion in the JUMP community. So in fact, so just to remind the context for everyone, so someone in the community just asked about an analysis of definitive screening design. And perhaps I can share my screen and the discussion, it will be easier for everyone. Let me check. So this is I hope you can see my screen.
Yes.
Yes, we can.
Okay, perfect. So this is the definitive screening design topic scenario. And so someone did a definitive screening design with 6 continuous factors. And so they choose a DSD with 17 run. And they had 3 additional runs at the 0 level. So they added 3 center points. And so this person was a bit surprised because with the DSD, you can detect or estimate a lot of possible effects because it can handle main effect, interaction effect, and quadratic effect. And in this scenario, he or she was a bit surprised because he or she was able to find good models for the response, and he was a bit he or she was a bit surprised to find this model very easily with this fit definitive screening model. And so his question was, okay, did I miss something? Perhaps it's more complex than what I thought, or is my model okay? And so a lot of people joined the conversation. So it was a very, let's say, intense discussion. So Mark Bailey also joined in. I think Bill also, you joined the discussion. So it was a lot of insight and exchange from everyone. And one of the possibilities that I wanted to emphasize on this situation, but also in DOE in general, is that you don't have I mean, it's difficult to find the perfect model, but there are a lot of possibilities to do in order to compare models and be more confident about the effect you have detected. So you can, for DSD or for other design, you can, of course, try different model and estimation methods. For example, in this example, this person has used the fit definitive screening model and estimation method, but you can also try fit least square. So this person was surprised about the result, and so a lot of exchange and discussion on this topic. So it was very interesting. I was mentioning Mark Bailey also jump into the discussion. Bill also who is here today, Frank Derick and others. So it was very interesting to have the insight and perspective from different people. And what I wanted to emphasize for design of experiment in general is that it can be quite tricky to find the perfect model, but most of the time you don't need to find the perfect model. You just need to be confident about the effect you have detected and that you suppose are active. And so the easiest way would be to simply try to have a look at different estimation methods. So for example, here, because it's a DSD, you can do fit definitive screening modeling. You can do also, I think I have the, yes. So fit definitive screening, so like this. You can do also a fit least square model. You also need to be more cautious, let's say, with the fit to level screening platform, because there are some assumptions behind. But sometimes for fit definitive screening design or for saturated, I mean, for design where you you inspect a lot of possible effects, but you don't have enough run to fit all of them. The fit two level screening platform can also be interesting. And for example, in this example, it just highlights 3 main effects. And you can also have a look at generalized regression or stepwise or other things. I would not recommend stepwise by default for comparing models because stepwise approach are, let's say, agnostic to the way you have design your design of experiments. Stepwise is more like a data mining approach where you try every combination of terms and everything and try to get the best model based on all this combinatorial calculation and effect entering and exiting from the model. But even if it's not very appropriate for DOE, stepwise can still be interesting. And that was, I think, my post from today. So just to show you, this is the kind of plot that can be helpful when you are investigating your design. And this is called a raster plot. This is something I have found in the publication from Peter Goose, Eric Schoen, and let me check. I think it was Alan Vasquez also. And so they use this kind of raster plot in order to have more confidence about which effect should be entered in the final model and which effect could be discarded. And I used this approach for this topic here, for this definitive screening design. And so basically, I think the question here was how to do it, how to do this plot. I don't know if the person who has asked the question can confirm this or not.
So if the person is present in here, maybe he or she would provide input. But I'm super interested to see how you get it.
Okay. Okay, so let's go for it in the meantime, I think. So it's quite some time that I didn't do it, so I hope it won't be too long and I will remember all the steps. Maybe I can also, it will be perhaps easier if I do, let's say, step-by-step post on this in the community so that everyone can also do it by themselves. Just to show you globally how it can be done. So basically, you will use the stepwise platform. So how to get to this, you will go to fit model. Then you specify, here I will specify all the possible effects that can be detected by my DSD. So it's main effect, two-factor interaction, and quadratic effect. So in fact, it's a response surface quadratic model. And I put here my response, so the target. And here in the personality, I will choose stepwise and click on run. So I will get to this here to this panel. And so how to get to this multiple model scenario. So first, I will change the rule here to Wall effect respecting heredity. So this is a kind of safeguard that we want to use because we suppose that DOE respects some principle, so effect heredity, effect hierarchy, and effect sparsity, meaning we suppose that for in design of experiment, there will be not so many effects. So this is effect sparsity. We also make the assumption that the effects in DOE are respecting heredity, meaning if you want a two-factor interaction to enter in the model, you need to have the main effect related to each of the factor in the two-factor interaction. And we also make the assumption that we have effect hierarchy, meaning main effect will have, let's say, a bigger impact on the response than two-factor interaction or higher order effects. So here we just change this rule to have, let's say, a kind of safeguard. For the topping rule, it doesn't matter, and the direction also, it doesn't matter, because we will use here in the red triangle option, the all possible models situation. And so here JMP asked me what is the maximum number of terms in a model. So here you can change. The higher the number of terms, the higher the number of combination you can do. So here in this example, because I wanted to have, let's say, a huge data set, and because I can handle, let's say, a high number of computation on my computer, I choose the number of terms in the model to 10, meaning half the number of rows in the design here, which is 20. So 10 terms possible. And number of best model to see, we can put the number we want. Here I will just specify 100. And we also have the possibility to check restrict to model where interaction implied lower order effect. So this is the heredity restriction that we wanted to have in the rules. So I will also check here. So here JMP creates an alert because with this combinatorial space, you can fit an exponential number of models. So depending on your computer, hardware, and so on, it can be more or less quick. Here, I think it will be quite quick, so some seconds. And so JMP has fitted a lot of models, and then he has ordered up to the best 100 models. And so you can see here for each of the model, you can see which terms have been entered in the model, what is the R square, the RMSE, and some information criterion. So you have a lot, in fact, you have a lot of data from the different models. And you can see here, he has fitted a lot of models with different number of terms. So here we have 4, then 5, and so on, up to 10, if I'm not mistaken. Yes, 10. And so at 10, you can see you have a lot of different terms possible. So main effect, interaction, and quadratic effects. And so we want to organize all of this in order to get the raster plot. So we will right-click here and click on Make Combined Data Table. And then we have something that is close to what we want to have. So we have here the model with the terms inside. And what we want to have is close to this, but not directly. Let me check. So the final data table should look like this. So the ID of the model, the number of terms, then the metric, and which terms are entered with the type. And so when we are here, there is something. So I think we have almost everything. No, okay. No, so here the problem is that the terms are listed all together, just separated by a comma. So we need to have a row for each of the terms for each of the model. So to have something like this, like for example here, you can see that this model, the 782, has quite a lot of different, has all the different terms here, but they are not all active. The presence of the term will be highlighted, let's say, by informed by this column presence 0 or 1. And so this is a tricky part because it involves a lot of data manipulation. So I will just try it in a few minutes, but if I don't remember the exact step, I will just write it down on a community post. I think it will not waste the time of everyone here. But I think it involves something like utilities, make indicators column, event column names. Yes, it looks like this. So now for each of the terms, you have a specific column with 0 or 1, depending if it's, so 0 is absence, 1 is presence. And so you have this for all of the possible terms in the model, so a lot of different columns. And because this is not very convenient for us, we want to stack all of this column together. So we will do table, stack, and we will choose all this. So sorry, I will do it more quickly. So we will stack all the indicator column of these terms here and click on OK. And so we have here you can see here the table that I used for the raster plot data table. So it looks a bit similar with the response and the different terms and so on. I think I did some changes by indicating the ID of the model because here you have everything and they are not listed by the model. So you need to group some of them together to indicate in which model it belongs. You have the label, so label is not important anymore, so we can hide it. Up. So data is in fact presence absence of the term. So here I'm not sure it will be correct because I don't have the ID of the model, but we can still try it. So sorry, I need to check. Okay, so model is yes. Yeah, and I did also something a bit more interesting. I use the recode part, and here you can save some time if you want to do it frequently. And you can do it through formula colon, but I used here the recode function, and for example, every time it's only factor 1 or factor 2 or factor 3, etc. I indicate that it's a main effect, and for others I indicate which terms it is. Yeah, no, sorry. I think yeah, I won't waste a lot of time because I think something was wrong here because the indicator column did not work well. So I think there is something I did before. I think it's text to colon. Yes, text to colon delimiter the comma here. Make indicator colon. Yeah, and here it works because what I did before was not okay because it didn't create colon for each of the terms. And here it works, and you can do the stack from here. So factor 1 up to this one, and it will look a lot better even if you don't have the ID for the yes. So here the label are the terms. So this is something you are interested in. And even if you don't have the ID for the model, I think that it will still look a bit better. BIC. Yes, no, I can't separate. No, I need I need an ID for the model. So this is something to do just before doing this, or else it won't work. Maybe there is something in JUMP to do an indicator colon quickly. I'm not familiar with this. But first, yes, you need to do an indicator colon because here it's one row, one model. So you need to create the indicator here. So 1, 2, 3, 4, 5, and so on for each of the model. Then create the indicator colon for the terms. Then stack everything. And when you have done this, you will have this kind of data table. And then you can do this kind of raster plot. So first, so for the terms, as I was mentioning, I indicate if it's a main effect, interaction effect, or quadratic effect. I also added a value order column property because it looks better on the graph. And so you can sort the order of the factor on the graph. So here from 1 to 6, and then the interaction following also the same ordering. Same also for the type. We want to see first the main effect, then the interaction effect, and then the quadratic effect. And so thanks to this value order property, when you do the graph, it will be already ordered, and you can also regroup some terms based on the effect here. And basically, the column you need to have is the ID of the model here. So just put it here. You need the terms here on the x-axis, and I also added the type of terms to separate main effect, interaction effect, quadratic effect here to have some kind of grouping. And you also need to use the data filter and to filter on presence equal to 1 in order to only see here the effect that are effectively present in the different models. And based on this, you can change the color here depending on your metric. So here on this kind of scenario, I choose information criterion like Bayesian information criterion or IKK information criterion corrected. And when you have done this, so you have this big plot, and sometimes it can be a bit tricky to see something because you have too many models here on the y-axis. So one simple things to do is simply to restrict. So for example, here I'm on BIC. You can restrict the number of model to only display, let's say, the model that seems the most appropriate. And when you do this kind of filtering here, only on the model that have the lowest BIC, so meaning the best compromise between prediction accuracy and complexity, you can see that you can find some pattern emerging, meaning in this situation, so the first 5 main effects seems to be quite interesting to investigate because always present in these models, and then it can be a bit more tricky to look at higher order effects. But you can also perhaps restrict a little more the number of models. And if you look at the best models, so here the model are ordered by the BIC ascending, so meaning the best model are here at the bottom. And if you look at the best model at the bottom here, so we have already talked about the main effect, but you can see, for example, here, this interaction seems to be quite present in most of the best model. This one too, so factor 1, factor 3, and factor 4, factor 5. And you also have 2 quadratic effects here that seems to be important. So this is an indication that maybe fitting a model with this effect could bring some good results. And what was interesting in this scenario was that with the raster plot, we were able to have the same result than what we get from the fit definitive screening, meaning the fit definitive screening platform identifies the first 5 main effects that we have seen in the raster plot. And when we look at the higher order effect, you can see that we have indeed these 2 interactions, so factor 1, factor 3, and factor 4, factor 5, and also the 2 quadratic effects for factor 2 and for factor 4. So it was a nice visualization trick, let's say, and something to get more confident when using a different modeling platform. And when you have some different results, it can also help to have this kind of visualization, so the raster plot, in order to discriminate the different models and understand which model does have the more sense, or which effect seems to be the most interesting to investigate.